Okay, so let's continue for another hour. So with that, the introduction about a plasma, length scales and time scales. Now I try to looking at the picture on the screen and how plasma is generated and transformed from an electrical field to an arc. So let's say you have a voltage, and this is a current. Initially, you apply a voltage to a mixture, and you start to see that the voltage is increasing and the current is increasing. They're because there are background ions and in the mixture. For example, in this room, you may have background electrons, background ions. You put an electric field, the current will increase, voltage will increase. But at a certain current, all the ions in that background are being used. So there's no more new electrons you can move. In that case, that the voltage keeps increasing and the current does not increase, right? So voltage keeps increasing and the current does not increase. But when the voltage becomes so high, and then some of the electrons is accelerate, gain energy, and they start to collide with a neutral molecules. They start to become a tungsten regime. That means electrons collide with a molecule, generate 2 electrons. That is the ionization process. They call it tungsten. So this ionization process, they just increase the current, and at the same time that the voltage increase is decreased. At a certain point, you see that the voltage becomes so high that a streamer flying from the electrode and to the mixture. So this is called corona. They generate this kind of streamer. So we'll talk about what is streamer, how they generate it. And then this streamer will die at the far field because there's not enough electrical field for them to continue. Just like a flame propagate and to the mixture, and then the surrounding of the mixture is very cold or mixture is diluted, they die. And then after that, if you continue to increase the voltage, suddenly that you generated the glow discharge. The whole volume start to glow like this. The streamer will not die, and the whole volume will start to glow. This is just like a fluorescent light bulb. It's just like a glow like this. And here is very ingredient. This is that the cathode, and this is that the bright ionization region. This is the dark region. This is that the positive column. So we'll talk about this. So this is a glow discharge, still volumetric, very volumetric. And here that if you increase the current, that the voltage start to decrease because more and more electrons is generated, that the resistance getting smaller, so the voltage decrease, current increase, right? But if you further increase that the power, then suddenly that this voltage increasing. It's because that the increase of electrons cannot satisfy the power increase because this is a cathode. It's very bright. They start to generate a second electron emission from the surface, this spot. They call this spot. They move around on the whole surface. And once the whole surface is covered and they don't have enough electrons to generate, then the voltage starts to current again. So they're hungry for electrons. So once the voltage becomes so high, and suddenly you generate a arc to start to form like this, and eventually become strong. Once the arc is formed, they generate enormous somatization. So here the ions electrons is generated by what? By collisional ionization. Here the electrons is generated by what? From the surface, cathode electron emission, second electron emission. Here is electron generated by what? By the thermalization. Because the gas becomes so hot, the electron just stripped by itself without electron collision, right? So electron impact, ionization, cathode, second electron emission, and then thermalized by itself. Do you understand the regimes? So now you start to understand the difference between plasmas, right? Now I try to come back to the first one. What is Townsend regime? Here. So if you have electrode, positive and 0, if you have 1 electrons, and they will collide with a molecule and generate 1 positive ion and adding another one. And keep doing this, and electrons getting more and more. This is like a chain branching process, right? And this electron it will move to the positive electrode and form a current that at a gamma electrons at D, the location of D, okay? And there's no positive electron, they want to move to the positive electrode. So gamma ID is 0, correct? And on the positive ions, they move towards the cathode, correct? And then they collide with the cathode, is gamma I at 0. And then if the energy is high enough, the strip electrons are out. This is called secondary electron emission. It's because that the ions bombard the surface, and then that energy is so high, they just strip electron out, correct? So this efficiency is 1 ion generate possibly a gamma electrons. No. 1 ion may generate 1 electron, may not. This is gamma. Gamma is typically less than 1.
So, is it like basically like a fission, but instead of neutron and fission, it's electron?
Yeah, it's just like that. It's not neutron, it's electron. Very good. So this gamma I call secondary electron emission coefficient. Remember? So this is that electron production in the gas phase, ionization. This is that electron emission from the electrode by secondary electron emission with ions. There's 2 different mechanisms. If that the electron number density is really, really low, it means that if the electron ion is very low, so the voltage is pretty much linearly dependent. In Poisson equation, the right-hand side is 0. If the second derivative equal to 0, that means the voltage is linear, right? It's easy. The linear electric field is constant. See what I'm saying? So now we try to understand what does it mean. Poisson equation is almost this. So now we try to understand the ionization process, that the flux of the electrons and change in a vertical direction and is proportional to the flux itself times that of the ion. It's just like combustion process, right? The change of the electron flux equal to the flux times that of the ionization, they call ionization coefficient. It's a laser absorption spectroscopy. It's the same thing. See what I'm saying? So this is easy. So you can solve this equation. It's so easy. Exponential function. It's same like a laser absorption spectroscopy, right? But this does not give you that the solution of this. In order to give you solution of this process, the ions come here, that this electrons has to be continually surprised. So that ion electron generation here has to be equal to this side. The continuation has to be satisfied. So now you can say at this boundary condition, that is a gamma E0 equal to gamma I0. So this is the, so therefore the current has to be sustained. And here, the electron flux has to be equal to the ion flux plus the electron flux from here. Ion flux coming from here, and then the electron flux is 0. If you substitute the 3 equations together, what do you get? You get that the alpha is that ionization coefficient times the distance between the electrode equal to log. At this condition, that the breakdown will happen. It's continuous, self-sustained. So this is called Townsend discharge, self-sustained conditions. This dictates at what voltage breakdown will happen. Okay, so let's continue this. Okay, this is the equation dictate that Townsend breakdown equations. So now we try to say, okay, so remember electron mean free path is lambda E. And then the electron energy with a mean free path must be the length times the electric field is that is the energy, the gain. So if you put that energy, you can say my alpha, which is ionization coefficient, is probably proportional inverse of the ionization in free path, mean free path. So this ionization free path must be proportional to that is the mean free path of electrons not every electron will be able to ionize it, so you have to form this Arrhenius law, right? So this is that connect alpha to that is the energy. Now we know that the mean free path is the inverse of pressure. The temperature is proportional to E over N. N is pressure. You substitute this into here and into there, you will find that the Townsend ionization coefficient alpha and the pressure has this relationship. And A and is from that the constant here, and B is from the constant there. So, and now that from equation 1 and 2, you substitute this guy, alpha, into that equation, this is what you get. The breakdown voltage is proportional to the pressure, and is proportional to the gap of the distance times the constant, and with a function about the ionization coefficient, and then the log pressure to the distance. This is that the very famous called a Princeton curve. The Princeton curve determines what is that the breakdown voltage as a function of pressure and distance, right? So if you're looking at here, that you can change the pressure. If you reduce the pressure, then you go into this direction. That means that the breakdown voltage is going to decrease. Why? Because if you reduce the pressure, the mean free path increase. The electrons gain more energy and easy to break down, right? So if you increase the pressure, otherwise, unfortunately, that you have to break. That's why at high pressure environment, it's very difficult to break down, right? That's why doing plasma, fluorescent light bulb is always almost a vacuum, right? So you understand that. But here, that if you could reduce the pressure, but if you make the distance is very small, you're going to this region. In this region, that the gap between the two electrodes is almost close to your mean free path. So electron does not gain the full energy before collide with the electrode, right? So now you have a voltage you have to increase dramatically in order to make a breakdown at a small gap. Understand? So this is the Townsend regime. And if you have a pressure is very, very high, what happens? Because there's so much ionization going on, and they generate a lot of charges. That charge itself, they can propagate by itself. So that created some kind of space charge region we'll talk about later. So this curve is clear for you? So now that everybody talking about breakdown, and you think about the Princeton curve. So the Princeton curve, if you measure it, and then these people compute it and measure it, you can see this is for different gases, hydrogen, argon, and nitrogen, they are different. Here is the minimum. That minimum is often used to control the plasma discharge. And so you can, using this Princeton curve to calculate the breakdown voltage, you calculate that the P over D minimum here, you can calculate that the optimum electric field of breakdown. Right. So it's very clear, very simple.
So what is the property in these gases that make these curves are different?
Well, because the ionization coefficient gamma is different, right? So, and now try to say, okay, now I explain you here, right? See what I'm saying? I'm explaining you what is Townsend regime here. So if that the plasma generates sufficient electrons, I'm saying sufficient electrons, that means that in some part, this is that the Debye range, this is that Debye range, and then in the middle is the neutral, that ions and electrons are equal. At an anode, you have more electrons. At a cathode, you have more ions. And now you start to say, because that in neutral, your electric field does not change. And near that a cathode, you got a lot of positive ions. They create enormous potential. And near this interface, you got electrons attracted here. You got potential decrease, and this is it. This is the perturbation about this charge distribution. Now, because you have more charge now, they perturb that the electric field, and then you can see at the cathode, electric field is so strong. You always, when you look at the plasma, you don't know which is cathode. You look at the luminescence. Luminescence, the strong part is the cathode, because the ions collide with the electrode, strip electrons, generate a lot of, and electric field is so strong at the cathode, right? So now you understand. When you look at the plasma pure mass, where is the electrode? Is the anode, and you can see the luminescence. So here, that is interesting. This is what we talk about, that is a breakdown due to tungsten regime, this here. So now we're talking about here, that is these coronas. So coronas is like a streamer. So that means that if your plasma ionization rate, the gamma is so large, so that or alpha is so large, you can generate a very high electric field. The electric field is so strong. If you put a needle with a very high electric voltage, and you can see there's a plasma formed from the needle just flash to the mixture. That is corona, right? So in that case, that you can see, so if you generate enough ionization, you generate positive and negative. The positive and negative, and this is external electric field caused by the V, and then electrons move to that direction, ions move that direction. If the charge is large, this separation creates internal electric field, right? This is called charge separation. This charge separation creates an internal electric field is E prime, and this E prime is due to that the charge is separate. And this charge separation creates a strong electric field between this positive and negative. You can see this is that the voltage is the potential. If this potential is electric field is strong enough, they can create breakdown there, right? So that is that. So the criterion of our streamer breakdown is that internal electric field is equal to the electric field of Princeton curve, right? Critical one. So once that charge separation becomes so huge, and this is typically the ionization coefficient times the distance is 20, and then equivalent to this much of number density. This is not much, right? It's less than half of ppm electrons. So then you start to generate this. Once you generate this, you can see the positive, positive streamers, the positive ions, they move this way, and the negative electrons, they're going that way. In this one, we call negative streamer because the electrons, they move very fast, and they gain energy, they ionize it, they generate electron ionization, tungsten ionization. But ions, they move very slow. They really cannot do anything. And but the ion-electron recombination, generate enormous energy and generate UV lights, right? Or the UV light. This UV light creates photon ionization. The photon ionization creates electrons. So positive streamer is photon ionization triggered. And then this one is electron ionization. So which one moves faster? What? Yes, electron move faster because they move faster. So this is what you see. You can see there's one electric field here, one electric field there. This is that So this is what happens here. And you can see that the coronas and moving and in the mixture. And this is in space, why that the spread happens. It's the same because that they have accumulated a lot of charge. The charge separation created an internal electric field so strong they can propagate by itself.
Does the molecular collision impact the field here?
Molecular collision does not. Only ionization process. Once it effect. So this is that the review paper and written by Peter, and you can see this is that they call electron avalanche, which is that the tungsten regime. This is the streamer. You can generate a positive, and the neutral afterwards. The positive charge just goes through, and people did some kind of simulation. They put a positive and negative electrode and do numerical simulation. You can see the negative streamer is spread, and positive streamer, and negative streamer is much faster, and then the positive streamers. So now you start to understand a little bit of plasma. Now, right? Correct? All right, great. And now you should start to see that the next regime, if you have a more current, and then then you form this kind of a glow. The glow, if you look at the electrode, and here that in this near electrode they call Aston start. Aston start because that the electron just come out from the surface. They have not gained energy yet. They cannot ionize anything. So therefore, you have a small dark area in there. But after they gain energy, and they call cathode glow, because this second electron emissions from the cathode, they gain enough energy, they collide and ionize it, then lose energy. Once you lose energy, then you go to this area they call cathode dark space here. That is a dark space. Again, electron doesn't have enough energy. They need to gain more energy to do this. So after that, you create this kind of a negative glow, is this bright spot, and that is that it generates a lot of ionizations there. And in this region, they call Faraday space. There's not much ionization there, but here is a positive column. Here, pretty much the quasi-neutral ions and electrons are equal. They're very bright and generate this kind of a stripe that is caused by plasma instability. So you can see that at the cathode, and ions move slowly. They got a lot of ions near the cathode. And electrons move so fast, you have little. So therefore, the current pretty much is dominated by the ion current. And in the neutral column here, everything is quasi-neutral. The electron number density is equal. This is a cathode. You have a very strong electric field near the cathode. And this is that the electric field in the column. And here, that the you have a very lower electric field because that is the diffusion of electrons, and two, that these places. And this is you understand this is very important to understand what is that the plasma you are doing. And then people doing the experiment is at Drexel University, Alex Friedman, they did this electrode, and you can see this is a cathode glow. This is a column, is that the positive column. You can change the pressure, you can change the different pattern of it. You can see all these things. And when you see this kind of is a non-equilibrium plasma. The electron energy is very high. So when you have a coronal discharge, now we say I have a sharp tip with metal. Coronal discharge means that occurs in a non-uniform electric field near a sharp point or edge of a metal, typically, so like this. So you create this kind of streamers and positive streamers with a photoionization process that can progress. So the corona means is a positive corona, for example, high voltage at the anode, and electron energy is very high, electron number density is not high. You have a negative corona, and they created at the high voltage by cathode. And this kind of corona, they develop when you have a stronger voltage, and then the corona grow, and then eventually they become a spark if there's a large current and enough electrons. And the arc is that ultimate thing the plasma want to be, because that's very stable, thermal equilibrium. Equilibrium is always loved by the system. So going this direction is equilibrium. It's just like combustion, right? If you burn everything go to water and CO2, because that is the equilibrium process. So you understand that the outer region, that means here, that you don't have much electric field, so basically your streamer die until that you have a very high current to create a channel. So streamer transition to arc is very important because you want to control the plasma, make sure they're not going to go to spark, because if you go to spark, then the channel is very small, unless you want to do combustion. Combustion you want to spark because you want high temperature and to ignite it. But for manufacturing, you don't, and want to spark. So the streamers can propagate at a million meters per second. And the diameter typically is at 100 micron to 1 millimeter. So the streamer is very fast. And then as the streamers approach the cathode, when this kind of streamers from the sky and initially catch the cathode, and then they create a very strong electric field between the streamer head and then electrode. So that strong electric field create a lot of breakdown and secondary electron emissions. And then the current quickly increase. The conductivity quickly decreased. So therefore, you create a flashback of the electron from this ground and to the sky, and eventually solenize it. And they call but anyway, so this kind of flashback from the cathode to the anode, it could be 10 million meters per second. It's close to light speed. It's very, very important. What I want to say that if you can do an experiment and measure the glow discharge, you can measure that the cathode and the column. And this, if you measure the temperature, vibrational temperature, and then the rotational temperature. Some people ask me what is the difference between vibration and rotation. But rotation is almost like a translation because one collision equilibrate them. But vibration and rotation, they are difficult. You need hundreds of thousands collisions in order to make it equal. So here the pressure, you can see at a lower pressure, vibration temperature is high, 4,000 Kelvin, and the rotation temperature is lower. But if you increase the pressure, that means it's more collision, more collision, more collision. Then vibration temperature is close to the rotation, eventually become equilibrium. So most of the interest today is try to people to do something that with a non-equilibrium, with high vibrational temperature, with a lower rotation temperature, so that it improves the efficiency. For example, you want to make ammonia, that the nitrogen molecules dissociate on the catalyst becomes so difficult. Can we excite that the nitrogen molecule by vibrational? When the vibration is so fast, they fall to the catalyst, just break down into two N atoms. That would be wonderful. And then the question that how do we vibrationally excite the nitrogen molecule to do that? How does the vibrational molecules interact with the catalyst if the catalyst has vacancy or without a vacancy? Is it titanium versus of nickel? There's a lot of interesting questions, right? And I'll come back to plasma. So spark, this is the engine, and you have a anode, you have an anode, you have a cathode, and then you generate an arc. Typically, that the arc is you have a very high current, and electron temperature is very low. It's about is less than 1 eV typically. And distribution function about ionization state of different ionization state is governed by the equilibrium called Saha equations. So this is very typical. I never want to study this because it's not much interesting. And actually, if you're writing a proposal about equilibrium plasma to DOE, likely you will be rejected because they think that just like equilibrium system is not much fun. And you want to do something non-equilibrium, like gliding arc, for example. If you have arc is formed, and here, the causing heat, the convection will make that arc move upward. When they move upward and they're getting longer, when you're getting longer, the resistance getting bigger, and the voltage is increasing, and the voltage is increasing, electric field is increasing, electric field is increasing, the electron energy is increasing. So the gliding arc is a transition from an equilibrium arc due to the cooling and the convection go to non-equilibrium. So this is that the high-speed image probably made by in Lund University. They collect all these things. This is my former graduate student right now in the CEFRC using this gliding arc. It's a magnetic field to make a gliding arc rotating around so that they can activate that mixture to see how that they change any chemistry and using a gliding arc. A gliding arc is between equilibrium and non-equilibrium. So they have the merits of high electron number density and high electron temperature, but not that high as a glow discharge. And this is that the gliding arc, if we write it down governing equation, that is Joule heating equal to the heat transfer, cylindrical coordinate. And then this is the relationship between voltage and work, and then the current. So you can, this is the conductivity of this here, is the Joule heating, the conductivity. And it's a Newton's equation. So you put this one into it, you can solve that equation. You can find that how that the heat losses from the column of this part of plasma is the surface area, conductivity, temperature gradient is equal to this. And with that, you can calculate that the voltage and then the current relationship. And for that, you can generate how does the current depend on the voltage, depending on the length scale or length of the gliding arc. You can plot the relationship about that the voltage as a function of arc length voltage and electric field at arc length. So this is that the very simple equation. You can do that. You can measure it. So a lot of people and has been measuring this. My student probably Tim Ravello and Zhongshan Li at the Lunde University. They measured this kind of a gliding arc. You can see this is arc. Some places the arc suddenly disappeared. It quenched. But then somehow later they reconnect it again. So because the arc want to be formed. So this is how the voltage change fluctuating as a function of time. So gliding arc is very interesting in terms of application, but very hard to study because they move in three-dimensional and the tiny of that arc, very hard to do using laser diagnostics to probe them, right? But it's interesting in terms of applications. So now that I come back to this curve, everybody in this room now understand what it is, right? So that is a very good. I don't want to repeat it anymore. So people these days are trying to do a dielectric barrier discharge because you don't want the plasma to be arc. In order to prevent the plasma to be arc, the only thing you want to do is limit the current. How do you limit the current? Well, you don't want into metal to metal. You cover one of the metal by dielectric materials so that you can limit the current. So you do this, you can see some kind of a dielectric barrier discharge. They make some kind of very uniform discharge. And this is that it looks very uniform, but if you measure the current, if you're using AC current, this is that the voltage, and this is that the current. You look at the current. The current is just a spike. Why does the current spike? Because of what? Yeah, a little bit of instability, but the mechanism is what? It's because of the streamers. Because when you high voltage, some of the charge, they just form on the surface, dielectrics, right? And the charge form electric field. When the electric field form a streamer, maybe likely will be a negative streamer. The streamer from that surface, top to down, they form one spike. You have many charges on the surface, they form a multiple spike, right? These are multi-streamer process. A typical dielectric AC discharge, it is governed by the streamers. And it forms some kind, looks like a uniform discharge, but the physics is very complicated and difficult to model because of the streamers, right? So this is the electron avalanche process. So, and then some people using nanosecond discharge. And why nanosecond? Because that you don't want that the energy to transfer to rotation and translational, somatization. You want energy to be just for vibration and then electrons. So the pulse is very short. Before the collision, a lot of collision happens, and then my pulse, my plasma is done. But let's say that this is the voltage, this is the time. This voltage, VB, is that the breakdown voltage of Princeton curve. We just learned, okay? If you put a voltage steady state, if you increase that voltage, and this voltage will break down. But in a nanosecond plasma, this voltage continue to go probably twice or even more higher before the breakdown happened. Why? Because when you have this voltage is created by nanosecond plasma, right? No, nanosecond pulsar. They increase the voltage so quickly, and then you start to develop this kind of tungsten. The tungsten is a collisional process. Imagine that this is 0.1 nanosecond. Even before the voltage rise to high voltage in 0.1 nanosecond before any collision can happen. So see what I'm saying? So therefore, that this TB is that T0 is that the time to static breakdown is here, but that this breakdown requires collision and tungsten breakdown, and that the ionization to grow. That's just like ignition process. You give me radical. If somebody gives you radical in nanosecond, can you ignite it in nanosecond? You cannot, because you need that the radicals to work with the combustion chemistry and get ignition to happen, right? This is exactly this is. You think that the voltage will break down. If you give the voltage very fast enough, they can't break down that voltage. This creates a very interesting phenomenon. Why? You can control the breakdown voltage, make the electric field much stronger than you want it. That means generate very high electron energy before breakdown happens. That increases the chemistry control, correct? So, and this is that the paper, and we published just a few months by my student Yiguang. You see, to control this, this is the electrode. I put a ferroelectric materials like PZT. Ferroelectric materials that you put electric field, they can generate a surface charge very quickly. The process to generate surface charge probably is a nanosecond or below, right? So if you put a surface electric field, and then with a ferroelectric charge, it quickly generates a strong surface charge. That surface charge will make that the breakdown. You can see the blue line, it is at the dielectric materials with ammonia covered on the surface. And then the red line, the yellow line, it is a ferroelectric discharge. You can see this is that the electric field, this is the breakdown happening. And suddenly that the electron emission. When the breakdown happening, that the ferroelectric electrode, they have twice of electric field than without ferroelectric materials. So now they create and then more interesting thing is that after because the ferroelectrics, after that the breakdown happening, if we cut off that the power, there's a lot of surface discharge. You can see that the emissions in the plasma continue to decay, but without ferroelectrics, everything will stop very quickly. You can dramatically extend that afterglow because of the surface charge. So this gives you a wonderful idea on how do you control plasma, isn't it? To understand the chemistry. All right, so I have to, so then other people want to say, okay, I don't want to use an electrode. I want to using some kind of electrodeless discharge. So that time, the people using, for example, high frequency, like a microwave or radio frequency. In there, that the frequency for radio frequency is 100 megahertz, and they can generate a captive discharge, we call it captive discharge, that the electrons is really not move from one electrode to the other. Instead, electrons just oscillate, and they create a energy coupling. And in other words, they also call inductive. They create a huge current and generate a magnetic field, and that create inductive heating. This one is almost like a thermoplasma now. So this is that a microwave can do the same thing. And a microwave, because that the frequency of the plasma frequency, if the microwave frequency is comparable or that is higher than the plasma frequency, you can generate a uniform heating and in a media. But remember, microwave itself is not uniform. It is a traveling wave. A typical with a wavelength at 2.4 gigahertz, that wavelength about a few centimeters. So in a few centimeters, the plasma is not uniform, right? But they can operate at atmospheric pressure. It's very convenient to use without the electrode. So let me try to stop here, and then people develop a micro discharge for biomedical applications, for a chemical manufacturing. Everything follows this Pearson curve, and so anyway, so what I try to summarize to you that a plasma is very interesting because that they create a non-equilibrium between electrons, vibration, and others. And also that the electron energy is so high that can you do something you don't. And so typically plasma become unstable is because you have electron number density. And if you increase the current, it's Joule heating, your temperature will rise. If the temperature rises, mean free path increase, number density decrease, and then your EV ends increasing, electron energy is gained, and you generate more electrons. This is the positive thing that drives this plasma instability. For example, the number density change as a function of time equal to the ionization process and then a recombination or attachment, loss of electrons. It's a producing and losing with a diffusion. So you can write down this diffusion term, just normalize using diffusivity with a thermal diffusivity. And then you write down that the length scale about diffusion is a lambda, just like flame thickness. So you can rewrite this a diffusion term with a diffusivity by a length scale of plasma with a number density. And this is a linear equation of plasma. And then you can write down that a number density of electrons proportional to initial number density exponential function. If this one is positive, that means instability will grow. If this one is negative, instability will not develop. So this is a instability theory in all plasma physics book, right? The question is that, where is combustion? There's no combustion here. So do you believe that if you're adding a combustion term, this instability will change? Will not. Well, I thought it will not change because plasma is, plasma people tell me, said, Yiguang, plasma is so fast. It's a nanosecond. Combustion is so slow. How could your combustion change plasma? Right? I believe that for many, many years, until a few years ago. I will show you later. So this is that the experiment I show you. This is that something called lightning, and so you're wondering why that the lightning really like that the volcanoes, and why does the lightning like that the oil field? It's not because that the oil field and then the volcanoes has unburned hydrocarbons. The answer is look at the experiment. So here is the experiment that you form a pentane with oxygen with argon. And you can see that if you put the fuel into the mixture, you start to see the uniform, and eventually go to instability. If you take that pentane away, what happens? Everything is uniform. There's no instability. So this is something very interesting and fascinating. I would say that how combustion affects plasma instability. I completely changed the people in plasma physics now. And they only say, oh, combustion, we have to study plasma. Combustion is just affected by plasma. Now I tell them, look, combustion changed plasma. Then start look, oh. So this is create a very interesting resonance. So plasma, they affect combustion. At the same time, I want to say combustion affects plasma. And plasma affects catalysis. I would say that catalysis affects plasma. So these are the interfacial research areas. It's very interesting. And a few experts, they understand both processes. Plasma combustion, plasma catalysis, this is a new area, it's growing. With that, I probably will switch to, I have 15 minutes. I have to continue to talk to the next one. So I finished that the introduction part of plasma, and then try to continue to what are the applications of plasma. So applications is always fun because you put a plasma there, you see something magically change. But the important thing is still the fundamentals. You understand how it is. So let's show you a big picture about that the plasma-assisted combustion, scramjet engines, spark ignition engines, flame stabilization, and ignition and cool flame stuff. And you see that how magically plasma can change. When I came to United States in 2001, at that time, the US does not want Russian scientists to go to China, and they give them the small grant, $50,000 per year. The only obligation for them to come to the AIAA meeting and to report what they have done. At that time, and I listened to all the talks about research in Russia, and they all like this. It's like a magic about plasma can do this, plasma can do that. I'll share with you. So plasma is basically that the motivation using a plasma to control flame instability and combustion efficiency so that it can develop new engine technologies or new fuels. So today you can see that we are running about that the hydrogen combustion, or we're running a very ultra-lean combustion to reduce NOx, and the fuel flexibility becomes very important with different heating values. So therefore, you need to stabilize that combustion process. And also that in detonation, rotation detonation or pulse detonation become interesting, but it's very hard to control that the detonation in a not fully mixed mixtures. And they often has the instability. I know internal combustion engine, how do you control an HCCI? How do you control enabling low temperature combustion so that it can reduce the heat losses? So these all provide opportunities for plasma to do something. For scramjet engine, for example, you want to fly Mach 10. And if you imagine that the engine length scale is about 1 meter long, so your flow time is about 1,000 meters per second. The flow in the engine is only 1 millisecond. And if you do combustion, you look at the ignition delay time, how much you can control the ignition below 1 millisecond. It's not easy, right? It's certainly not easy. And certainly you have to, not only just ignition, you have to complete the whole combustion process so that there's no incomplete combustion. So that is a tough thing in terms of using hydrocarbons as a fuel. So therefore, you develop some kind of a plasma-assisted ignition for flame stabilization to overcome, to accelerate combustion and to stabilize. So ignition is controlled by residence time, normally by ignition time scale, which is a function about pressure and equivalence ratio and temperature. And you want that the Duncker number to the order of 1. Flame stabilization is also a combustion time scale, which is different from ignition. You also want the Duncker number to be close to 1, so that, or larger than 1, so that you can burn it. And plasma can provide a wonderful opportunity to accelerate ignition by order of magnitude. And can also create flame stabilization by accelerating combustion process. So when I was a graduate student at your age, that scramjet engine becomes very hot. And because Reagan president, they want to develop a space plane. So everybody wanted to do a supersonic combustion. My PhD thesis was supersonic combustion. So this is that people would do. They either put a cavity here so that they create a recirculation zone so that you can enhance combustion in a supersonic flow to make the Duncker number is large. Or you can using a shock wave, induce the shock wave. This shock wave create a pressure range, you enhance the recirculation, you can stabilize the flame. And the person who first one to using plasma in a scramjet engine was Kimura. And then they put a plasma torch into the supersonic flow and try to stabilize the combustion process. And that triggered a lot of interest of plasma assisted combustion in scramjet engine. So if we're looking at the ignition and flame speed, they are a function about equivalence ratio, temperature, activation energy, and strain rate of a flow. And so, for example, this one without plasma, flame will be blowout. With plasma, you can stabilize it. It's stabilized either by many ways. By one way is that you increase the temperature, that increase Arrhenius law. The other way that you increase ionic wind, because when you generate the charge is the move that collides the flow. They create this ionic wind at maybe a couple of meters per second. You can break down the fuel from larger ones to small ones, increase the diffusivity. So that is, but all this thermal effect, ionic wind effect, fuel fragmentation effect is well understood. And the most important thing is how does ions, radicals, and excited states, they affect combustion chemistry, they increase the reaction rate or reduce the activating energy. That is not clear. Yeah, for example, if you have a singlet oxygen, for example, O2 singlet, react with methyl. What is the reaction rate? Is that reaction rate the same as ground state, or is it 10 times higher? Probably it's 10 times higher to do that, because the O2 singlet is almost 1 eV, 1 electron volt, and energy there. So you can dramatically reduce the energy barrier. So these are the cool things a lot of people are using. Today, electrified manufacturing, people are doing the same thing, but not with oxygen anymore. It's more because maybe CO2, maybe hydrogen, and then how does that excited hydrogen and CO2 can help to reforming about the syngas, or making methanol, or making ammonia. So that are the hot topic today. But it's the same thing. Plasma is plasma, no matter what you change, and it's the same thing. So this is that a modeling about ignition. So this is that if you your model, for example, is that the hydrogen combustion. So without a plasma, so you probably ignition delay time is very, very long. But if you using plasma generated, for example, atomic oxygen, you can dramatically accelerate ignition. What if the ignition delay time is accelerated so much, they are even shorter than the combustion time? So then the curve, S-curve, starts to shift like this. If the curve is accelerated, become like this, that means there's no extinction. Anything you put it there, they will burn, but may not immediately burn. But this is how the plasma can do the thing, right? They may not accelerate flame speed, because plasma does not generate that much radicals for you to create heat release. But they can accelerate ignition. Ignition doesn't need many radicals. So that's what I'm saying. Every time when you say ignition is a problem, you should think about plasma, because they can accelerate orders of magnitude about that. So same thing experiment, and we did at Princeton. You can see that it was methane ignition, and you can see this OH radicals as a function of fuel concentration. So you can see this kind of S-curve in combustion. But if you increase the oxygen concentration with plasma, everything becomes monotonic. That means that you can stabilize the combustion without any extinction, or the ignition dictate. So I think that in combustion field, and there's a flame stabilization in gas turbine, right? You have a flame, they have much swirling. And most people believe that flame stabilization is because of the flame speed with flow, right? When the flow speed is larger than flame speed, and they will, but flame speed is very hard to increase, to be honest. Turbines can do it. But flame speed can be easily increased if the flame is an auto-ignition assisted flame. You see what I'm saying? If you enhance ignition so much, just like this is the ignition assisted flame. If the ignition assisted flame, the flame speed can be what? Hundreds, 1,000 meters per second. Detonation is typical, is ignition assisted flame, right? So using plasma to control the ignition, to make that the flame as ignition speed, ignition assisted flame propagation, you can stabilize that combustion. For example, in the cavity, if you have plasma, you can accelerate the ignition in the cavity that makes that the combustion is ignition assisted, then you don't worry about the flame stabilization issue. But many people, including in GE and many others, they don't understand this concept. Everything always look at the flame speed. Yeah, the very classical thinking. Chemistry and ignition play a much bigger role. So, and plasma jet ignition. So let me see whether, okay, I formulated. So when you have a plasma jet, that electrons collide with, for example, methane, they generate ions and also generate radicals. And they break oxygen into two radicals and N equal to 2 N atoms. All these processes are so fast. Fast means one electron collision will make it happen. So electron collision is more than 10 to the 9th per second. So this process is so fast. So that gives you a dramatic ignition delay time, dramatic acceleration with the same energy by heating it compared to the plasma. The red one is by plasma, and the black one is by heating. So you rather using that the energy using electrons instead of using heating, you can accelerate the ignition process. So here that is a supersonic combustion process. You have a hydrogen and flowing with air. You have plasma torch. As you can see, as you increase the plasma torch, that the leading shock wave is getting stronger in the channel. This is because combustion shock train coupling. You have more heat release, supersonic flow. It does not look like anyone to perturb the flow rate. If you have combustion generate heat, that means you have pressure wave generation. that the supersonic flow will form a shock wave in strong to recover the pressure and to make the flow go through. Unless you have a combustion is so strong that makes the shock wave form here, they propagate upstream, that is engine unstart of scram jet engine, right? So using plasma to control reactivity and control the engine is a promising way and in supersonics. So people try to using equilibrium, non-equilibrium. For example, plasma torch is not something very energy efficient because just heat everything. But people try to using, for example, using this kind of dielectric barrier discharge, for example, in the recirculation zone, and create the high electron density. As you can see from here, that by increasing that the plasma power, and they can increase that the pressure recovery. That means enhance the combustion process. So let me see the DBD, dielectric barrier discharge with high electron energy. They can enhance that heat release rate and enhance the flame stabilization in the process. So let's take a break, and then we come back and for 11:15.